Welcome back, aspiring cybersecurity professionals. I'm your instructor, and you're tuned into episode 3 of our comprehensive cybersecurity course. In our previous episodes, we laid a crucial foundation. Episode 1 introduced you to the vast and dynamic world of cybersecurity, defining key terms and the importance of this field. Episode 2 then delved into foundational concepts, discussing threats, vulnerabilities, risks, and some initial defense strategies. We talked about how vital it is to understand the landscape before we can secure it. Today, we're taking a deep dive into what is arguably one of the most fundamental pillars of cybersecurity, networking fundamentals. Think about it, almost every interaction we have online, every piece of data we send or receive, every attack or defense, happens over a network. Without a solid grasp of how networks function, understanding cybersecurity is like trying to navigate a city without knowing how the roads work. That's why today's episode, Networking Basics Every Hacker Must Know, is absolutely critical. We're going to demystify complex networking concepts, breaking them down into easily digestible parts. Specifically, we'll explore the conceptual brilliance of the OSI model, the practical application of the TCP/IP model, the difference between IP and MAC addresses, and critically, how data actually travels across the vast expanse of the Internet. By the end of this episode, you'll have a hacker's mindset when looking at networks, identifying potential points of interception, analysis, and vulnerability, as well as the knowledge to defend against them. So, get ready to connect the dots, literally, as we unravel the intricate world of computer networks. Let's begin. Before we dive into the technicalities, let's establish why networking is the bedrock of cybersecurity. Imagine cybersecurity as the art of protecting a city. If you want to protect a city, you need to understand its infrastructure, its roads, bridges, power lines, and communication systems. In the digital world, networks are those roads and bridges. They are the pathways through which all information travels. Without a network, there's no internet, no online banking, no social media, no cloud computing. And where there's communication, there's potential for interception, manipulation, and exploitation. Most cyber attacks, whether they're phishing campaigns, malware infections, denial of service attacks, or data breaches, fundamentally rely on network communication at some stage. Attackers exploit vulnerabilities in network protocols, configurations, or devices to gain unauthorized access, steal data, or disrupt services. If you understand how data is supposed to flow, you can identify when it's flowing incorrectly or being rerouted maliciously. You can pinpoint where an attacker might be trying to listen in, where they might try to break into a system, or how they might try to block legitimate traffic. Conversely, for defense, a deep understanding of networking allows us to design secure network architectures, implement robust firewalls and intrusion detection systems, and effectively respond to network-based threats. It allows us to segment networks, encrypt traffic, and monitor for suspicious activity. So, for both offensive and defensive cybersecurity, networking isn't just a desirable skill, it's an absolute prerequisite. It's the language of the Internet, and to secure the Internet, you must speak its language fluently. To understand how networks operate, we first need to grasp a core principle: complexity management through modularity. Sending a simple email or streaming a video might seem straightforward, but behind the scenes, it's an incredibly complex dance of technologies. To make this manageable, network communication is broken down into smaller, discrete functions. Think of it like building a house. You don't just start with a completed house, you have architects, plumbers, electricians, carpenters, and painters, each responsible for a specific aspect of the construction. They follow a specific order and a set of standards. Similarly, in networking, different tasks are handled by different layers or components. This modular approach offers several key advantages. It simplifies design, facilitates troubleshooting, allows for specialized development at each layer, and promotes interoperability between different vendors' equipment. When you send data, it doesn't just travel as one big block. It's fragmented into smaller pieces, each piece handled by different networking rules and devices, before being reassembled at the destination. This systematic breakdown is what models like the OSI and TCP/IP aim to illustrate. They provide a standardized way to describe and understand the processes involved in network communication, making it easier for engineers, developers, and cybersecurity professionals like us to analyze, design, and secure networks. These models are essentially roadmaps for how data travels, and understanding these roadmaps is your first step towards mastering network security. Let's start with the grand conceptual framework, the OSI model. OSI stands for Open Systems Interconnection. Developed by the International Organization for Standardization, or ISO, it's a theoretical model that describes how different network systems can communicate with each other, regardless of their underlying hardware or software. It's not a protocol itself, but rather a universal standard that allows diverse systems to interoperate. Think of the OSI model as a blueprint for communication, much like an architect's blueprint for a building. It divides the complex task of network communication into 7 distinct layers, each performing a specific function and communicating only with the layers directly above and below it. This separation of concerns makes it incredibly powerful for understanding, troubleshooting, and securing networks. While it's largely theoretical and not directly implemented in real-world protocols like the Internet, its conceptual clarity is invaluable. It helps us categorize different networking technologies, understand where certain attacks occur, and where specific security controls should be implemented. We often use the acronym, "Please do not throw sausage pizza away," or "All people seem to need data processing," to remember the layers from bottom to top or top to bottom. Let's briefly list them from layer 1 to layer 7, physical, data link, network, transport, session, presentation, and application. We'll now break down each layer, explaining its function and relevance. Let's begin our journey through the OSI model from the top, the layers closest to the user. Layer 7, the application layer. This is the layer that directly interacts with the user's software application. It provides network services to end-user applications. When you open your web browser, send an email, or use an instant messenger, you're interacting with applications that operate at this layer. Protocols here include HTTP for web browsing, FTP for file transfer, SMTP for email, and DNS for domain name resolution. From a cybersecurity perspective, this layer is a frequent target for attacks like SQL injection, cross-site scripting, and phishing, as it directly handles user interaction and application logic. Layer 6, the presentation layer. This layer is responsible for data translation, encryption, and compression. It ensures that data sent from the application layer of one system is readable by the application layer of another system. For example, if you send an email with an encrypted attachment, the presentation layer handles that encryption and decryption. It also deals with data formatting, like converting character sets or images. Protocols like SSL/TLS, which encrypt web traffic, technically operate across the presentation and session layers, ensuring secure communication. Understanding this layer is crucial for securing data in transit and ensuring its integrity and confidentiality. Layer 5, the session layer. The session layer establishes, manages, and terminates communication sessions between applications. Think of it like a conversation manager. When two applications need to communicate, the session layer sets up a session between them, keeping track of who is talking to whom, ensuring that the dialogue is orderly, and closing the session when the conversation is complete. This layer handles tasks like authentication, authorization, and synchronization, ensuring data is transferred in the correct sequence. For instance, when you log into an online banking portal, the session layer helps maintain your active login session. Session hijacking attacks, where an attacker takes over an authenticated user's session, directly target this layer. These three top layers work in concert to prepare user data for its journey across the network and to interpret incoming data for the applications. Now, let's move to the heart of the network communication, layers 4 and 3. These are particularly critical for cybersecurity. Layer 4, the transport layer. This layer is all about reliable and efficient data transfer between end systems. It segments data from the session layer into smaller units, called segments, and then reassembles them at the receiving end. The transport layer also handles error checking and flow control. Its two most important protocols are TCP and UDP. TCP, or Transmission Control Protocol, is connection-oriented and reliable. It establishes a connection before sending data, acknowledges receipt of packets, and retransmits lost packets, ensuring that all data arrives in order and without errors. Think of sending a certified letter, you get a confirmation of delivery. This is used for applications where data integrity is paramount, like web browsing, HTTP, email, SMTP, and file transfer, FTP. UDP, or User Datagram Protocol, is connectionless and unreliable, but much faster. It sends data without establishing a connection or guaranteeing delivery. Imagine sending a postcard, you just send it and hope it arrives. This is suitable for real-time applications where speed is more important than guaranteed delivery, like streaming video, online gaming, and voice over IP, VoIP. From a security standpoint, understanding TCP and UDP ports is fundamental. Firewalls operate heavily at this layer, allowing or blocking traffic based on port numbers. Layer 3, the network layer. This layer is responsible for logical addressing and routing. Its primary job is to move packets from one network to another, finding the best path, or route, through a collection of interconnected networks. The most well-known protocol at this layer is IP, or Internet Protocol. IP provides logical addresses, known as IP addresses, for each device on the network. Think of an IP address as a postal code and street address for your computer. Routers, which are specialized network devices, operate at this layer, directing packets to their destination based on these IP addresses. Without the network layer, data couldn't travel beyond its local network. Attacks like IP spoofing, where an attacker disguises their IP address, and various routing attacks, directly target this layer. Understanding IP addressing and routing is absolutely essential for network diagnostics, security incident response, and designing secure network segments. We're now moving to the bottom two layers, which deal with the nitty-gritty of local network communication and the physical transmission of data. Layer 2, the data link layer. This layer is responsible for node-to-node data transfer. It ensures that data is transmitted reliably across a specific physical link, typically within the same local network segment. It takes the packets from the network layer and encapsulates them into frames. The data link layer has two sublayers. Logical Link Control, LLC manages communication between higher layers and the lower MAC sublayer. Media Access Control, MAC controls how devices on a network gain access to the medium and transmit data. It uses unique physical addresses, called MAC addresses, which are hard-coded into network interface cards, NICs. Think of a MAC address as your device's unique serial number or physical street address within a small neighborhood. Switches, common networking devices, operate at this layer, forwarding frames based on MAC addresses. Attacks like ARP spoofing, where an attacker links their MAC address to another device's IP address, or MAC flooding, which overloads a switch, directly exploit vulnerabilities at the data link layer. Layer 1, the physical layer. This is the most fundamental layer, dealing with the actual physical transmission of raw bit streams over a physical medium. It defines the electrical and mechanical characteristics of the network. This includes the cables, twisted pair, coaxial, fiber optic, the connectors, wireless signals, voltages, data rates, and how bits are represented as electrical signals, light pulses, or radio waves. Devices like hubs, repeaters, and network interface cards operate at this layer. Essentially, it's about converting the zeros and ones into a format that can physically travel across the network medium. While it seems basic, even this layer can be targeted. Physical layer attacks involve things like wiretapping, cutting cables, or electromagnetic eavesdropping. Ensuring the physical security of your network infrastructure is therefore a crucial, though sometimes overlooked, aspect of cybersecurity. Together, these layers complete the journey of data, from your application down to the physical wire, and back up again on the other side. While the OSI model is a fantastic theoretical framework, the Internet, as we know it today, primarily runs on the TCP/IP model. TCP/IP stands for Transmission Control Protocol/Internet Protocol, and it's a more practical, four-layer model that evolved from ARPANET, the precursor to the Internet. Unlike the OSI model, which was developed before the Internet was a widespread reality, the TCP/IP model was designed with specific protocols and real-world implementation in mind. Think of the OSI model as the detailed theoretical blueprint for any building, while the TCP/IP model is the practical construction guide for this specific house that we call the Internet. Let's look at its four layers and how they map to the OSI model. 1. Application layer. This layer combines the OSI model's application, presentation, and session layers. It handles high-level protocols that interact directly with the user's application, such as HTTP, FTP, SMTP, DNS, and SSH. All the applications you use daily that connect to the Internet operate here. 2. Transport layer. This layer is essentially the same as the OSI transport layer. It's responsible for end-to-end communication between applications, using protocols like TCP for reliable, connection-oriented data transfer, and UDP for faster, connectionless data transfer. 3. Internet layer. This layer corresponds directly to the OSI network layer. Its main job is logical addressing and routing of packets across different networks. The Internet Protocol, IP, is the most crucial protocol at this layer, responsible for assigning addresses and ensuring packets find their way to the correct destination, often across multiple hops. 4. Network access layer. This layer combines the OSI data link and physical layers. It deals with the physical transmission of data frames over a specific network medium, including hardware addressing, MAC addresses, medium access control, and the physical characteristics of the network interface. Ethernet and Wi-Fi are examples of technologies operating at this layer. The TCP/IP model is robust, flexible, and scalable, which is why it has become the universal standard for Internet communication. For cybersecurity professionals, understanding the TCP/IP model is not just academic, it's essential for analyzing network traffic, identifying attack vectors, configuring security devices like firewalls and intrusion prevention systems, and effectively responding to incidents that occur at different layers of the network stack. When we talk about Internet protocols, we are almost always referring to TCP/IP. Now, let's talk about addresses, specifically, IP addresses, which are fundamental to how data finds its way across the Internet. IP stands for Internet Protocol, and an IP address is a unique numerical label assigned to each device connected to a computer network that uses the Internet Protocol for communication. Think of it as the digital postal address for your computer or smartphone on the Internet. It allows other devices to send data packets specifically to your device. There are two main versions of IP addresses we need to discuss, IPv4 and IPv6. First, IPv4, Internet Protocol version 4. This is the version you're probably most familiar with, even if you didn't realize it. An IPv4 address is a 32-bit number, typically represented in what's called dotted decimal notation. This means it's broken into 4 sets of 8 bits, or octets, each ranging from 0 to 255, separated by dots. For example, 192.168.1.10 or 8.8.8.8, Google's public DNS server. IPv4 addresses are classified into different types. Public IP addresses. These are globally routable addresses assigned to devices directly connected to the Internet. They must be unique across the entire Internet. Your home router typically gets a public IP address from your Internet Service Provider, ISP. Private IP addresses. These are non-routable addresses used within private networks, like your home or office LAN. They are not unique globally, but only within their local network. Common private ranges include 10.0.0.0/8, 172.16.0.0/12, and 192.168.0.0/16. Your computer or phone in your home network will likely have an IP address like 192.168.1.5. How do devices with private IPs access the Internet? Through a process called Network Address Translation, or NAT. NAT allows multiple devices on a private network to share a single public IP address when connecting to the Internet. Your home router performs NAT, translating private IP addresses to its public IP address and vice versa, making it appear to the Internet that all traffic is coming from a single source. From a cybersecurity perspective, understanding IPv4 addresses is crucial for network scanning, identifying targets, analyzing logs, setting up firewall rules, and understanding network topology. Attackers frequently use IP addresses to identify victims, launch targeted attacks, or disguise their own origin through techniques like IP spoofing. As we just discussed, IPv4 addresses are 32-bit, meaning there are only about 4.3 billion unique addresses. While that sounds like a lot, with the explosion of Internet-connected devices, computers, smartphones, smart home devices, IoT sensors, we've largely run out of available IPv4 addresses. This scarcity is a major driver behind the adoption of IPv6, Internet Protocol version 6. IPv6 addresses are 128-bit numbers, providing an astronomically larger address space, approximately 340 undecillion addresses. To put that into perspective, it's enough to assign a unique IP address to every grain of sand on Earth, and then some. IPv6 addresses are typically represented in hexadecimal format, grouped into 8 sets of 4 hexadecimal digits, separated by colons. For example, 2001:0DB8:0000:000:8A2E0370734. While IPv6 adoption is still ongoing, it's the future of the Internet, and cybersecurity professionals must be prepared to work with both IPv4 and IPv6 environments. Many modern operating systems and network devices now support both simultaneously. Now, let's switch gears to another critical type of address, MAC addresses. MAC stands for Media Access Control. While IP addresses are logical and can change, e.g., when you connect to a different network or your ISP assigns a new public IP, a MAC address is a physical, hardware-level address. It's a unique identifier permanently burned into your device's network interface card, or NIC, during manufacturing. A MAC address is a 48-bit number, typically displayed as 6 pairs of hexadecimal characters separated by colons or hyphens, like 00:1A, C2:7B, 00:4C. The first half of the MAC address identifies the manufacturer of the NIC, and the second half is a unique serial number assigned by that manufacturer. The key difference: IP addresses operate at the network layer, layer 3, and are used for routing data across different networks, global routing. They're like your mail address, guiding mail to your house. MAC addresses operate at the data link layer, layer 2, and are used for delivering frames between devices within the same local network segment. They're like the specific apartment number within your building. When your computer wants to send data to another device on the same local network, it uses the Address Resolution Protocol, or ARP, to resolve the destination device's IP address to its MAC address. Knowing MAC addresses is important for network forensics, access control lists on switches, and identifying devices on a local network. Attackers sometimes spoof MAC addresses to bypass network access controls or remain anonymous. Understanding both IP and MAC addresses is fundamental for diagnosing network issues and implementing layered security measures. We've covered the theoretical models and the addressing schemes. Now, let's bring it all together and visualize how data actually travels across the internet, using the principles we've discussed. Imagine you're sending an email from your laptop to a friend's server across the world. 1. Application layer, laptop. You hit send in your email client. Your email application, e.g., Outlook, passes the data to the application layer protocols like SMTP. 2. Transport layer, laptop. The SMTP data is passed to the transport layer, where TCP takes over. TCP segments your email into smaller pieces, adds a TCP header, with port numbers for your email client and the server, sequence numbers, etc., and ensures reliable delivery. 3. Internet layer, laptop. Each TCP segment is then passed to the internet layer, where IP takes over. IP adds an IP header to each segment, turning them into IP packets. This header contains the source IP address, your laptop's IP, and the destination IP address, your friend's mail server's IP. This is the crucial routing information. 4. Network access layer, laptop. These IP packets are then handed to the network access layer. Here, they are encapsulated into frames by adding a data link header, which includes your laptop's MAC address and your router's MAC address, and a trailer. These frames are now ready for physical transmission. 5. Physical layer, laptop. Finally, the frames are converted into electrical signals, light pulses, or radio waves, and sent out through your laptop's Wi-Fi card or Ethernet cable. The signals travel through your local network. Your home Wi-Fi router, acting as a switch for local devices at layer 2, receives the frames and forwards them. As the data leaves your local network and heads towards the broader internet, it hits your router's gateway interface. The router's role, your router, operating primarily at the internet layer, examines the destination IP address in the IP packet header. It looks at its routing table and determines the best next hop, which other router on the internet it should send the packet to. The router then re-encapsulates the IP packet into a new frame appropriate for the next physical link, e.g., from your home network to your ISP's network. Across the internet, this process repeats across potentially many routers. Each router acts like a traffic cop, reading the IP destination and directing the packet towards its ultimate goal. This involves what we call hops. At each hop, the data link header is stripped off and a new one added, but the IP header remains largely intact until it reaches the destination network. Arrival at destination. Once the packet arrives at your friend's mail server's network, the process reverses. 1. Network access layer, server. The incoming electrical signals are converted back into frames. The data link header is stripped off, and the IP packet is extracted. 2. Internet layer, server. The IP header is examined to confirm the destination IP address matches the server. The IP header is then removed, revealing the TCP segment. 3. Transport layer, server. The TCP segments are received. TCP checks for errors, reassembles the segments into the original data stream, acknowledges receipt, and passes the data up. 4. Application layer, server. Finally, the data is delivered to the mail server application, SMTP server, which then stores the email for your friend to retrieve. This entire journey, often involving multiple networks and devices, happens in milliseconds. Understanding this full flow, the encapsulation and decapsulation at each layer, and the role of devices like switches and routers, is absolutely critical for identifying where vulnerabilities might lie, where traffic can be intercepted, or where security controls like firewalls need to be placed. To illustrate the practical importance of understanding these layers, let's consider a common network security incident, a distributed denial of service, or DDoS, attack. The goal of a DDoS attack is to overwhelm a target server, service, or network infrastructure with a flood of traffic, rendering it unavailable to legitimate users. Attackers often leverage a botnet, a network of compromised computers, to launch these coordinated attacks. DDoS attacks can target various layers of the OSI or TCP/IP model. Layer 7, application layer, attacks. These are sophisticated attacks that target specific application functions, such as repeatedly requesting a resource-intensive page on a website or attempting to log in multiple times. For example, an attacker might flood a web server with legitimate-looking HTTP requests, but at such a high volume that the server's processing power is consumed, preventing it from serving real users. Defending against these requires web application firewalls, WAFs, and sophisticated traffic analysis to distinguish legitimate user behavior from malicious automation. Layer 4, transport layer, attacks. A classic example here is the SYN flood. Remember the TCP three-way handshake? A client sends SYN, synchronize, request, the server responds with SYN ACK, synchronize acknowledge, and the client completes with ACK, acknowledge. In SYN flood, an attacker sends a massive number of SYN requests to a server but never sends the final ACK. The server keeps waiting for the ACK, tying up its resources for half-open connections, eventually exhausting its connection table and refusing legitimate connections. Firewalls and intrusion prevention systems often have SYN flood protection. Layer 3, network layer, attacks. These attacks focus on overwhelming network infrastructure like routers or the network bandwidth itself. An ICMP flood, ping flood, is an example, where an attacker sends a large number of ICMP echo request packets to a target, consuming bandwidth and server resources as the target attempts to respond. This directly targets the internet layer and can disrupt routing or consume all available bandwidth. Understanding which layer an attack targets is vital for effective defense. If you're facing a SYN flood, you know to look at your transport layer defenses, firewall rules, TCP stack hardening. If your web application is slow due to excessive HTTP GET requests, you know to examine your application layer defenses, WAFs, rate limiting. This layered understanding allows cybersecurity professionals to diagnose issues, apply the correct countermeasures, and design resilient network architectures from the ground up. It's about not just reacting to an attack, but understanding its mechanics and pinpointing its origin within the network stack. Knowing these concepts theoretically is one thing, applying them practically is another. Let's look at some simple commands you can run on your own computer to see these network fundamentals in action. First, to identify your own device's IP and MAC addresses, you can use, on Windows, open command prompt and type IP protocol configuration/all. This command will show you your device's IPv4 address, default gateway, your router's IP, and, importantly, the physical address, which is your MAC address, for each network adapter. On Linux or Mac OS, open terminal and type ifconfig, or IP address show on newer Linux systems. This provides similar information, your IP addresses, subnet masks, and MAC addresses for your network interfaces. This directly demonstrates how your device has both a logical, IP, and physical, MAC address. You'll notice your private IP address, like 192.168.x.x, and your router's IP, which is your gateway to the internet. Next, let's explore how data travels by tracing a route. On Windows, use tracert followed by a domain name, for example, tracertgoogle.com. On Linux or Mac OS, use traceroute followed by a domain name, for example, traceroutegoogle.com. This command shows you the path that packets take from your computer to the destination, listing each hop or router along the way, along with their IP addresses. This graphically illustrates the Internet layer, Layer 3, in action, showing how routers direct your packets across the internet. You can see how many different routers your data traverses to reach even a seemingly close destination. Finally, for basic connectivity testing, the ping command, like ping google.com, sends ICMP, Internet Control Message Protocol, echo requests to a destination and measures the response time. This helps you confirm if a host is reachable on the network and how quickly data can travel to it. These simple commands are fundamental tools for any network administrator or cybersecurity professional. They allow you to diagnose connectivity issues, verify network configurations, and even perform initial reconnaissance on target networks, all built upon the foundational knowledge of IP addresses, MAC addresses, and how data travels through network layers. Practice these commands on your own system. Understanding their output will solidify your grasp of networking fundamentals. We've covered a substantial amount of ground in this episode, laying the essential networking foundations for our cybersecurity journey. Let's quickly recap the key takeaways. 1. The OSI model is a conceptual framework with 7 distinct layers: physical, data link, network, transport, session, presentation, application, that helps us understand how network communication logically works. While theoretical, it provides a powerful way to categorize network functions and analyze vulnerabilities. 2. The TCP/IP model is the practical, 4-layer model: network access, internet, transport, application, that the internet actually runs on. It's more streamlined and protocol-centric, making it crucial for real-world cybersecurity analysis. 3. IP addresses are logical addresses. We discussed IPv4, the 32-bit addresses prevalent today, and IPv6, the 128-bit future-proof solution designed to handle the explosion of internet-connected devices. IP addresses are essential for routing data across different networks globally. We also touched upon public versus private IPs and NAT. 4. MAC addresses are physical, hardware-level addresses burned into network interface cards, NICs, used for communication within a local network segment. They are distinct from IP addresses, which are logical. 5. We walked through how data travels across the internet, emphasizing the process of encapsulation and decapsulation at each layer, and the roles of devices like switches and routers in guiding data from source to destination. For cybersecurity, understanding these concepts isn't just academic, it's operational. Attackers exploit vulnerabilities at specific layers. Defenders implement security controls at these very same layers. From identifying attack vectors like IP spoofing or MAC flooding, to configuring firewalls, analyzing network traffic, or responding to DDoS attacks, a deep understanding of networking fundamentals is your most potent weapon. It equips you with the mental model to dissect complex network issues, troubleshoot effectively, and build robust, secure network infrastructures. This knowledge forms the bedrock upon which all advanced cybersecurity concepts are built. And that brings us to the end of episode 3, a crucial step in your cybersecurity education. You now have a foundational understanding of how networks are structured and how data flows, which is truly empowering. But our journey doesn't stop here. In the next episode, episode 4, we will build directly upon this networking knowledge by diving into network security devices and protocols. We'll explore the tools and technologies that actively protect our networks, such as firewalls, intrusion detection and prevention systems, IDS/IPS, virtual private networks, VPNs, and other essential network services like DNS and DHCP, and how they contribute to a secure network posture. This will bridge the gap between understanding how networks work and understanding how to protect them. Don't miss it. If you found this episode valuable, please give it a thumbs up, subscribe to the channel for more in-depth cybersecurity content, and hit that notification bell so you don't miss future episodes in this structured course. Your comments and questions are always welcome below. I read them all and love engaging with you. Share this course with anyone you think might benefit from learning cybersecurity. Thank you for joining me, and I look forward to seeing you in episode 4, where we continue to unravel the fascinating world of cybersecurity. Stay safe, and keep learning.